Thanks, everybody. Okay, so extremal graph theory as a topic is absolutely vast. So I'm actually going to focus, because it's only a few lectures, on a specific aspect, which is extremal numbers. So the extremal number of, and shout at me if I'm writing too small. So the extremal number of a graph H is the largest number of edges in an n-vertex graph that doesn't contain a copy of H. Number of edges in an n-vertex H-free graph. Okay, so a lot is known about this function, particularly for graphs, and a lot is not known as well, especially if you go to hypergraphs. So the basic result in the field, which goes back to 1907, is a result of Mantel. I think it was actually so it's in a Norwegian journal, and it's actually in the journal as a problem. So just as a sort of a fun problem. But the result basically states, so in these terms, it states that the extremal number of K3 is equal to the floor of n squared over 4. Okay, so that doesn't really give much away. So seeing this formula doesn't tell you very much. But the extremal example, the thing that's actually the example for this is you take two large blobs and you put all of the possible edges between these two blobs. So every edge from the first part to the second part, and this doesn't contain a triangle because, well, a triangle would have to have two vertices in one of these parts, and that's, you're not going to have that edge. And the way you optimize the size of this, so the total number of edges, is you make the two sides as equal in size as possible. So just make one the floor of n over 2, and make one the ceiling of n over 2. Okay, so I'm not going to prove many of the basic results in the field, but just to give you some feel for what's going on, let me prove this result. You've probably seen it before. It's a fairly easy exercise once you have the right idea, but let me give at least one proof. Okay, so let's suppose G is a graph, is an n-vertex graph with no copy of K3. Okay, so what do we know about this? Well, let's also, within this, let's take a largest possible independent set. So let A be a largest independent set. So what I mean is largest set containing no edges inside of itself. Then what we know is that if I look at any particular vertex, then because it's triangle free, if I take a vertex V, then the neighborhood of that vertex is also an independent set. So if there's an edge in here, we have a triangle, so there can't be an edge in there. So that means that the neighborhood of this, so the degree of V, is less than or equal to the size of this independent set. So we know that D of V is at most A for every V. So, and V is just the set of vertices of G. Okay, how can we use that? Well, another thing that's true of this A is that if we let B be the complement of A, so let B be the complement of A, then every edge within the graph actually touches B, because they're not completely contained in A because it's an independent set, so they have to touch B. So every edge in G touches B. Basically, you have A, you have B. We know this is an independent set. We don't know anything about this thing yet, but we know there's no edges in here, so either you're getting edges across here or you're getting edges in here. In either case, you're touching B. Okay, so that allows us to give a bound on the number of edges. So the number of edges is at most, the sum over all v in B times d of v. Okay, because every edge has at least one endpoint in B, I pick up all edges this way. In fact, if there was any edges in B, I'll pick them up twice. So actually, sorry, this is a less than or equal to. So the number of edges is definitely at most this thing. And unless B is an independent set, it's actually equal. But this is definitely an upper bound. Now we also know, because we just showed it here, that actually d of v is always at most a. So this is at most a times b. And, okay, now let's do the AMGM inequality on this. This is at most a plus b over 2, all squared. A plus b, well, a is a set, b is its complement, so they add up to being n, so this whole thing is n squared over 4. Okay, and that's it. So that's the entire proof. Every proof of this needs somehow something like this fact. But you see, in the end, it just amounts to some elementary thing. And actually, if you analyze the equality cases here, well, for equality to hold here, these need to be as close in size as possible, either equal or different by 1. And for this to be an equality, you need this to be empty. So actually, in the end, it tells you that that is the extremal structure. Okay. So how does this generalize? Is there a duster somewhere? Oh, sorry, yeah. Okay, so the generalization of this was proved quite a bit later, actually. So in 1907, Turan's theorem was proved in 1941. And Turan's theorem basically generalizes this to all larger cliques. And the statement is as follows. Okay, so the extremal number now of the complete graph with OR vertices, so this is again the complete graph with OR vertices, is at most 1 minus 1 over OR minus 1 times n squared over 2. This isn't always exact, but basically the thing to keep in mind is that the worst possible example is to take a collection of sets. You're taking OR minus 1 parts, you put all the edges between the parts, and then you choose these to be as equal in size as possible. So they're all either n over OR minus 1 floored or n over OR minus 1 ceilinged. And then that's the example. The proof of this, there are ways to generalize this proof. I've written some notes, and I've spelled out the proof of that in the notes. Okay, but again, this is the picture to keep in mind. Generalization of this, not long after, due to Erdős and Stone, it's sometimes also called the Erdős-Stone-Szymonovich theorem, who observed the chromatic number connects to it, is that the extremal number of a general graph H is actually 1 minus 1 over the chromatic number minus 1 times n choose 2. So up to some little O factors, and those little O factors can cause trouble, but if you forget about them, then it's saying that it's n choose 2 times the proportion of the edges is basically what you get with this kind of picture, except now this gets replaced by the chromatic number minus 1. So this is the chromatic number. And again, it's easy to see that this is best possible, because if you take a construction like this, if it has chromatic number h, you can't possibly embed it into something that only has h minus 1 parts. You need, if you have chromatic number h, that means you have to have that many independent sets partitioning the vertices. Okay, so that's a very important theorem. That basically answers the question, or seems to answer the question completely for graphs. There is this little issue here of what's going on, but there's kind of two directions you can go from here. So we have mean, there are lots more directions, and people have explored lots of variations of this, but the sort of two main directions that people have gone in are, well, look at what happens for hypergraphs. So you can ask exactly the same question for hypergraphs. You fix some 3 uniform hypergraphs, so where the edges have size 3. And then you ask, well, how many edges can you have without containing such a thing? And the answer is basically we don't know. We have no good idea. In his original 1941 paper, Turan asked about just a tetrahedron. So this is what's called a K43. But basically all 4 faces of tetrahedron. There's a conjecture that the answer, in terms of proportion, the answer is 5/9, but that's wide open. There are some approximations using what's called flag algebras, but nobody really knows the answer. There have been some breakthroughs with regards to hypergraphs in determining densities for other graphs and so on, but in general, it remains wide open as to what's happening there. I won't talk about that. That's a course in and of itself, and actually, there are other people probably at the program who could talk more knowledgeably about that than me. What I am going to talk about is what happens for bipartite graphs. Okay, so, well, I said here this kind of solves the problem, except if it's the case that the chromatic number is 2, then this becomes 1 minus 1 over 2 minus 1, so 1. This just becomes 0. And the main term is this. So here we just have, so from Erdős Stone, we just have that the extremal number of any bipartite graph is little o of n squared, which isn't a very precise result. It could be something else. It could be n times log n or n to the 3 halves or something. And what I'd like to talk about is what actually is it. So what can we say about what it is? What do we know? We actually don't know a lot, but I'll try and tell you at least some of what we know. Okay, so the first result in this direction is a result of Kuvari, Schoch, and Turan from the 1950s. I always forget whether it's 1953 or 54 because my dad was born one year and my mother the other. So, but let's say 54. And what it says is, so in a way, you know, complete graphs are like the basic graphs for bipartite graphs, where you just have 2 parts and all the edges go between. In that case, the basic graphs are complete bipartite graphs. So you have KST, where you have S vertices on one side, T on the other, and you put all the possible edges between. So that's the most basic bipartite graph, and in a sense, well, every other bipartite graph is obviously contained within one of these things. So if you can say something about the extremal number of these things, you've said something about the extremal number of all bipartite graphs. So, so the result that they proved is that if S is less than or equal to T, then the extremal number of KST is at most some constant depending upon S and T times n to the 2 minus 1 over S. Okay, so you get actually, instead of this little o n squared here, you actually get a power saving. So you get a reasonably good power saving. So for example, if it's K22, then you're getting 2 minus a half, which is 3 halves. And we'll come back to that. So one corollary of this is that for all bipartite H, there's some delta such that you get a power saving. Okay, perfect. Okay, so that tells you there's a power saving. But now, having done that, the question that always happens in extremal combinatorics is, you get some bound, how sharp is it? Like, can you get closer in on that? So the question is, what's the correct exponent? So given a h, what is the exponent that we need in order for this to go through, for this to be true. All right. So let me prove this result, because it's a very basic result, and it's kind of a model for the kinds of arguments that we use in other situations. So, so what we're going to show is that the extremal number satisfies this. So again, suppose G has n vertices. Let's give it a certain number of edges. So C times n to the 2 minus 1 over s edges. And let's suppose it has no KST. Okay, so it's sort of, we're assuming it contradicts the statement. C is some large thing. If it has that many edges, and we're assuming it doesn't contain it, and we'll show that it actually does. All right, so what we're going to do is we're going to double count some specific thing. So we will double count so count in two different ways. Things of the form Vs, where V is a vertex, S is also a collection of vertices that has size D, and V is joined to W for all W in S. Okay, so the picture is just, you have some vertex V, you have it's connected to a collection of things which we call S, and S has size, sorry, did I say D? I meant, this is little s. Okay, so the point is, the reason that we're counting these things is that if we can actually find T vertices here that all have the same neighborhood, then we actually have a copy of this KST. Okay, so one thing is just giving you a K1S, but if we have T of them, then we're in good shape. We have the thing we're looking for. In fact, that gives us one of the bounds. So we have an upper bound for these collections so upper bound for the number of these tuples. And the upper bound is, well, the number of ways to choose S is just n choose S. So n things, we're choosing S things out of them. And my claim is that the number of V's connected to that is at most T minus 1, because if it was T, then we'd be done. So, as otherwise, we have a KST. Okay, and just let me upper bound this. This is at most T minus 1 times n to the S divided by S factorial. So that's a very easy exercise. All right. We'd also like a lower bound for this. So how do you count these things? Well, a different way of counting these things is look at each vertex and then just look at the number of S tuples contained in its neighborhood. So we also have a lower bound. And the lower bound, in fact, this is an exact bound, which is the sum over all V of dV choose S. You look at a vertex, you look at its neighborhood, and you choose each of the possible S tuples is actually giving you one of these things. All right, this looks like something that might be hard to handle, but we can use some convexity. We can basically say that this is, that basically the average of these things is greater than or equal to, the average of these binomial coefficients is greater than or equal to the binomial coefficient of the averages. So this is at least, I should put a 1 over n here. This now. Okay, but this I understand. The sum over V of dV is actually just twice the number of edges, and the number of edges is this. So this is actually just this times this choose S. Okay, so that's just substituting in and using the fact. So what I'm using is the sum over V of 2V is just twice the total number of edges. If n is large enough, and let's assume n is large enough, it sort of makes life a little bit easier, then this is at least n times this thing to the power of s divided by s factorial. And that, just expanding it out, that is n c to the s, n to the s minus 1 over s factorial, which is c to the s times n to the s over s factorial. Okay, so now we're bounding this quantity. We have an upper bound, we have a lower bound. It's upper bounded by this, it's lower bounded by this. So if c is too large, this is a contradiction. So if this c is too big, then you end up with something larger than t minus 1. So if c is greater than t minus 1 to the 1 over s, then we get a contradiction. So in that case, we just stick that in here. We get that this is bigger than t minus 1, but that's bigger than the upper bound. So the original assumption that we don't contain a KST must have not been true. Okay. So that's basically the proof of that. It's quite simple. It's doing this double counting. Essentially what it's doing, you're counting the number of stars, so that's what this thing is. And then you're saying, well, each of these s tuples is contained in at most t minus 1 of these stars. Okay, we'll see other arguments like that later, where we count things, just some basic unit, and then we multiply it in some way. All right. So the question on everybody's lips now is this sharp? So when is this actually the correct bound? So in their original paper, they conjectured, so Kovari, Shosh, and Turan, KST. I'm not sure if this is true or not, but often complete bipartite graphs are written as k, little s, little t. And I think it might be because of the names. But anyway, this conjecture is that this bound is sharp, that this KST is always at least some c prime, depending on s, times n to the 2 minus 1 over s for s less than or equal to t. And this has been one of the main motivating conjectures in studying these bipartite extremal numbers, is to actually try and get this. Now, since the 60s, we've known that this is true for s equals 2 and s equals 3. I'll describe the constructions now, but we don't really know it for anything else. And in fact, I think there's a consensus forming now that it's probably not true, but probably very difficult to prove. So let me give the example for s equals 2. In fact, it's with no, basically as soon as you show you have something with no k22, then it obviously doesn't contain k23 or k24, any of these larger things. So the example is, it works over finite fields. So you have fq. So in fact, let's just work over prime fields. So that's really just the collection 0, 1, 2, up to p minus 1, which has addition and multiplication. So a very basic thing. And the actual example is over fp squared. So, and that's just the vector space over fp. So on the one side, we have, so we form a bipartite graph between fp squared and another copy of fp squared. This corresponds to the points. So this is the points of fp squared. This corresponds to the lines. So essentially, maybe I have to leave out 0, 0 here. Actually, let me just drop 0, 0. But this is the line. And if I'm given a point AB, then I form the line AX plus BY is equal to 1. So So all the points on the line are all of the x and y's, which satisfy ax plus by equals 1. So here I have points, here I have lines. They basically have the same indexing set. What I do is I join a point to a line if the point is contained in the line. So if we have a point here and a line here, then this line is joined to everything that's actually on that line. And that's all I'm doing. I'm connecting lines to all of the points that are contained in that line. And this doesn't contain a K22 for a very simple reason, in that if I have two lines, then they can intersect in at most one point. So any two lines intersect at most once. So there's no K22. Because a K22 really does consist of, 2 points, or two things on the right-hand side corresponding to lines, which have 2 points in their common neighborhood. But if your common neighborhood are each lines, and they intersect just once, then that can't possibly happen. I should say, this is all lies coming from our intuition over the real numbers. This is true over the real numbers. If you have two lines, they intersect at most once. It is also true within finite fields, that particular thing, but you have to be careful about proving it. It's not an obvious transference thing. You actually need to verify that it's true. I say that because the next example, that's actually important. So for s equals 3, you do something very similar. So the example for K33, you have fp cubed on this side. Again, it's all the points in here. You have fp cubed on this side. This, again, corresponds to points. This corresponds to unit spheres. So given ABC, the unit sphere that I go to is x minus a squared plus y minus b squared plus z minus c squared equals 1. And the way to think about this is, again, I have spheres on this side, and these spheres are connected back to everything that's on that unit sphere over here. So each vertex corresponding to a sphere is connected to all of the things on that sphere. And again, if you think about what happens over the real numbers, if we have 3 unit spheres, well, the first 2 unit spheres will intersect in a circle, so just some circle somewhere. The third one coming in, if I have a sphere and I have a circle, that circle can only intersect the sphere twice. Okay, so actually 3 spheres intersect 3 unit spheres, careful about that, intersect at most twice. And that's good because it means there's no K33. Because 3 points on the right corresponding to spheres intersect in at most 2 points. So there's no K33. The thing I should say for each of these is that the number of points is correct. So over here, the number of possible edges, well, every p squared edges here has all of the things on a line over here, so it's connected to p things. So you get p cubed edges, but p squared is equal to n, so this thing is n to the 3 halves. And over here, there's some similar analysis, which I won't go through, but the number of edges is, again, n to the 5/3. So you really are getting the correct number of edges in these things. In fact, the things in the notes, I've written down ones that aren't bipartite. They work, and they have exactly the right number of edges. OK, so the thing about this, which I flagged over here, is that you really have to be careful about this. So the thing of unit spheres and the reals intersecting at most twice is not true in fp cubed unless you choose p carefully. So you actually have to choose p congruent to 3 mod 4. Otherwise, if you choose p congruent to 1 mod 4, there's actually a large line or a large plane contained in these things. OK, so this looks good, right? We have intersections of lines here, intersections of spheres here. So now you just choose the next thing for 4, and then you're done. except that doesn't work, or it kind of doesn't work. So these two constructions are from the 60s. The next result was proved in the 90s by Kolar, Ronyai, and Sabo. And it says that the extremal number of KST is greater than or equal to some constant depending on S times n to the 2 minus 1 over S. And this is for right. Okay, so it turns out we can prove this, but we can only prove it if T is way larger than S. So in these particular cases, if S was 2, we could take T as 2. If S is 3, we could take T as 3, which is optimal. In general, we can't do that. And the first thing that was proven, the first existence result of any sort, was proven by Kolar, Ronyai, and Sabo, who proved that it was sufficient to be larger than S factorial plus 1, which is pretty large. This was then improved, so their construction, it actually follows the feeling of this. You have to choose the right collection of algebraic surfaces, essentially. And you show that their intersections are bounded using Bézou's theorem. What they do is more complicated, but this is the basic idea. And then you get this band coming out of it. This was improved a little bit later with Noga alone on board. They got this down to S minus 1 factorial plus 1. So this is some projective variant of this. This is already interesting because it actually matches the bound for 2 and 3. So if you put in S equals 2, 2 minus 1 factorial is 1, so 1 factorial plus 1 is just 1. So you get S and T are both 2. For 3, this is 2 factorial plus 1, again 3, so that's good. But actually the best that's known still for 4 is K47. So we know that K47 satisfies this band, but we don't know K45 or K46. For a long time, it was maybe thought that maybe these are optimal, maybe there's some nice thing happening. But very recently, a very nice paper of Boris Buch, using what's called the random algebraic method, got this down to exponential. So these bounds are super exponential. They're something like S to the S. This is some constant to the S. This is quite difficult. It uses something called the random algebraic method, which I will talk about the next day, but I'll give a much more basic version rather than what Boris did here. And this is the lie of the land. So the conjecture, the original conjecture, is that actually you can take T equals S. This is saying that, well, you can take T to be at most exponential in S. And I think it's probably one of the more important questions in extremal graph theory to figure out which of these is correct, or if you can get anywhere closer to this. Anyway. Okay. Again, within the notes, I've said something about what's happening here. So I've said something about this bound. Maybe I put in this bound. It uses some algebraic geometry, but it's relatively simple. But I won't talk about it now. All right, what I do want to talk about is the other basic thing within the area, which is, so the two classical things that people had studied, which had bounds going back to the 60s, were these complete bipartite graphs, this thing, and cycles. So there's a theorem of Bondi and Shimonovich from 70s, I think. I won't say exactly when, giving a nice upper bound for the extremal number of even cycles. So this is a cycle with 2k vertices. And they proved that this is at most some constant depending on k times n to the 1 plus 1 over k. The feeling here is that complete bipartite graphs are quite dense, and you need the bound to be actually quite high, quite close to 2. Cycles, and the longer they get, the sparser they get. So they're quite sparse, they get sparser, and the bound is actually getting very, very close to n to the 1 plus 1 over k. So somehow, even cycles, the longer they get, the easier they should be to embed. So that's kind of what this is saying. I'm not going to try and prove this. It's actually surprisingly, well, it takes some work to prove in general. What's much easier is to prove it if instead of looking for cycles of length 2k, you look for cycles of length at most 2k. So let's so the claim is that the extremal number of NC, let's abuse notation and call it this, is at most ck times n to the 1 plus 1 over k. I'm going to use another slight thing that's not obvious, but is a standard tool in the area, which is a theorem due to Erdős and Samotij. So this is a theorem of Erdős and Samotij from 1966, which says, basically, I'll state it in a sort of rough form, but this is the spirit of the thing. So in studying extremal numbers, and this is sort of needed for the problem set as well, so we can assume that the max degree isn't that much bigger than the minimum degree. This is not generally true for extremal problems, but within the context of extremal numbers, you can do this. You can assume that if the minimum degree is something, the max degree isn't that much larger. And this is an important basic result in the area that's very, very useful. Okay, so in particular, we know that, so if G has n vertices and at least some c times n to the 1 plus 1 over k edges, then we can actually assume that the minimum degree is pretty large as well. So then we can assume that delta of G is at least some constant prime times n to the 1 over k. So this is saying that the average degree is at least 2c times n to the 1 over k. This is just passing, using that lemma there to pass to a graph where we can assume that the minimum degree is also large. All right. Why do I do this? Because I want to count paths of length k. And a useful thing when you're counting paths of length k is to be able to just do it greedily. So let's count paths of length k. Okay, so if you're going to form a path of length k, you have to start somewhere. So start at a particular vertex. Sorry, this should be walks, because I'm going to allow them to self-intersect. But start at a vertex, and then choose a neighbor, and then choose another neighbor, and choose another neighbor, and so on. Here, I have n choices here for this. I now have at least delta choices here for this. I now have, well, at least delta choices here for this, at least delta choices here for this, at least delta choices here for this. So that's just the basic version. That allows them to self-intersect. If I don't want them to self-intersect, I can be a little bit more careful. So if I want to go back to paths, then I have n choices to begin with. I have delta neighbors here. I now have delta minus 1 choices for the next one, because I don't want to self-intersect here. And I keep going. So delta minus 1, delta minus 2, and so on, up to... Okay. So going back to paths, the total number of paths is at least n times delta minus 1 times delta minus k plus 1, which is at least, if n is large, this is at least n delta to the k over 2. Okay, so actually quite a lot of these things. But I also know this delta is at least this. So actually it turns out that the number of paths of length k is at least n delta to the k over 2. And just sticking in this bound, that's at least c prime to the k times n squared over 2, which is bigger than n squared if c prime is large enough. Okay, so the whole point of this, the whole reason I did this, was to get a lot of paths. So I want at least n squared paths of this variety. Okay, so why n squared? Because now, if I fix two endpoints, there are n squared, well, there's n choose 2 choices for endpoints. How many paths will there be between those? Well, because of this, there has to be more than one path between two endpoints. So therefore, there's some pair UV with more than one path between them. So you have U, you have V, you have a path of length k, you have another path of length k. That second path of length k might intersect the first one. So if the two paths didn't intersect, I have a cycle of length 2k, and I'm done, okay, which would be great. But this argument, which is just relying upon a simple counting argument for the number of paths, all it tells us is, well, there's two paths, so they might intersect. But if they intersect, that gives me a cycle of length shorter than 2k. So I'm still done. So that implies a cycle of length less than or equal to 2k. It could be 2k, but it also might be shorter than 2k. But that proves the result, the claim over here. Getting rid of this restriction, this less than or equal to 2k, requires a sort of bespoke argument to the context. Sorry, Bryce? Yeah, you only needed the lower bound, but I sort of included it because on the problem set, you actually do need it. So, but it's a useful thing to have in your toolbox anyway. So there's a few different bespoke arguments for getting cycles of length exactly 2k, but the real problem is trying to avoid degeneracies, trying to avoid that these paths overlap with each other. And that problem sort of permeates through the study of extremal numbers, where it's very easy to show that there might be degenerate copies of some things, but trying to get non-degenerate copies is the problem. Anyway, we'll come back to that again. All right, so again, when are these results tight? So when, for which k is the extremal number, and now let's go back to the actual cycle, at least some constant depending on k times n to the 1 plus 1 over k. It's a good question. We really don't know. So it's known for k equals 2, k equals 3, and k equals 5. So there's a slightly strange thing where it jumps k equals 4. So what we're saying is we know the bounds for C4. We've done that already, actually, because C4 is the same as K22. So a cycle of length 4 is the same thing. C6 and C10. But C8 we don't know, and C14 we don't know. And actually, again, I sort of think, especially for C8, I don't necessarily think this is the correct bound. Okay, so one thing that is known, and this is an analog of the Kolar-Ronyai-Szabo result. So let's let theta of KL be the graph consisting of L vertex disjoint paths, well, internally, vertex disjoint paths between two vertices. Okay, so a picture is worth 1,000 words. You just fix two vertices, and you put a path of length k, and another path of length k, and another path of length k, and so on. So this would be a theta k5, because it has 5 paths of length k going between two vertices. The special case where L is 2 is the same as a cycle. So C2k is this. The analog of the result of Kolar, Ronya, and Szabo is a result of mine saying that, so this is a theorem by myself, saying that, so for every k, there exists L such that the extremal number of n theta kl is equal up to some constants, some theta, depending on k and l, of n to the 1 plus 1 over k. This just means up to some constants, it's equal to that. So even though we can't prove for cycles that this is the correct bound, we can show that if we're willing to take a bunch of paths between two vertices, then this is the correct bound. But in the same way, this is very similar in some ways to this Kolar, Ronya, Szabo thing of getting a large KST, except now we're getting many paths between vertices. Okay, so the last thing I want to say a little bit about is what the constructions are for this. Why is it 2, 3, and 5? So okay, so let's take a graph. So what we're going to do is consider, again, FP now to the k, and the collection of lines of the form, we're going to do x plus y, 1 z, z squared up to z to the k minus 1, for y an element of fp, and x is itself an element of fpk, and z is an element of fp. Okay, so what is this? All right, so what it is let's just look at what happens in fp cubed. We have fp cubed, which again is just a sort of finite box, 3 dimensions. This is some collection of lines. Basically, between any point, given any point, there's going to be a collection of lines of this form, depending on z going through it. So you'll get one line here, another line here, another line here. And they follow something called the moment curve. So the collection of points, collection of lines going through a particular point sort of twist in some way. So this is what's called the moment curve. And now, it bears some similarity to what we had before, because we have some collection of points, we have some collection of lines, and then we join them if one is contained in the other. So we have n equals p to the k points, n equals p to the k lines. We take points over here. We take lines over here. So we have some point here, some line here. And we join them if and only if, so P is joined to L, if and only if P is contained in the line L. So it's very similar in some ways. The K22 example we gave earlier was lines. We joined lines to the things containing them. This is the exact same, except now we don't take all lines. We just take some collection of lines. So you have to be careful about the collection of lines you take. I won't go through all the details of this now, but again, I've written it down in the notes. But the point of this is that basically this construction only works in the case where k is 2, 3, and 5. So this contains no C2k, but it works only for k equals 2, 3, and 5. So if you look at the notes, you'll see why that's the case. But now, this construction, this specific construction was discovered in the 90s by Wenger, but actually people in finite geometry, which is a field that's at the interactions of algebra with these kinds of finite constructions, knew about these kinds of constructions back in the 60s. So for example, the k equals 3 constructions are connected to what are called generalized quadrangles. And there's something called the Veit-Thompson theorem. And the Veit-Thompson theorem says that these generalized polygons, as they're called, only exist for these values, essentially. So at least coming from the algebraic side, there's good reason why these things exist. Now, on the algebraic side, these are very rigid structures. Within extremal combinatorics, we don't care so much about rigidity, so it's still possible that these things exist, but we don't know. And again, like this KST question, this is probably one of the main questions in the area. Okay, I could say more, but I'll stop there. Thank you.